How's it going? How are you guys doing today? Thanks, Mike. I just want to keep playing guitar. I love Ventura Highway. Okay, better put this down. Okay. But we still need some background music. I mean, come on. Gotta have something. Okay, well, I hope everybody's doing well today. Oh, that was a little loud. Oh, this thing isn't plugged in yet. Where'd you go? Okay. So, I thought we would start off today, since we're getting down to the end. I thought we'd start off with making a flow chart that kind of ties together all of the different concepts from this class. And maybe puts it in a nice context for you that helps to connect everything and connects it to what we're doing right now. So, follow along with me. This is one way of connecting the different ideas from dynamic systems that we've worked with. Okay. So, we want to model... Wait, first I want to say this. No. We'll draw it. We have some real life system. And I'm going to put like a fuzzy, like cloudy boundary around it. And what that represents is that real life things are kind of complicated and they're hard to completely characterize. And what we're doing in dynamic systems is we're trying to make a real life system more concrete so we can understand it. And the way we do that is we apply some lens to this real life system, and I'm going to call that lens physics, like the physical laws, and that helps us to make sense of these observations of what goes on around us. So, for example, to model a real-life mechanical system, in this class we've used Newton's laws. We say that the sum of forces acting on the body should be equal to the mass times its acceleration. Or if the body's rotating, the sum of moments acting on the body is equal to the moment of inertia times its angular acceleration. Or if it's an electrical system, we have different electrical laws like the capacitor element equation, the inductor element equation. We have the we use the loop rule, Kirchhoff's loop rule, to understand a circuit. Okay, so we use the lens of physics to make a mathematical model for this real life system. And I'm going to put a clean square box around this. And that's as opposed to like this cloudy shape around the real life system. Because once we say, okay, I'm substituting in my mind this mathematical model for the real life system. Well, mathematical models are very clean, at least the type that we're working with. And they're very well understood. And then they put reality into this very clean box. And so we've done some examples of real life systems in this class. Like we did an RC circuit. We did an RLC circuit. We looked at a pendulum. We've looked at a motor. And we've applied this lens to each of those systems, and we came up with models that pretty well describe the real life behavior, but it's not exactly the same thing. So I want you to recognize that limitation. Now, there's different types of mathematical models. But the type that we work with in this class we work with a subset which are called linear time invariant, meaning they don't change with time, linear time invariant ordinary differential equations. We've just been calling them differential equations. But it's good to know that, you've heard of nonlinear equations. Maybe you've heard of partial differential equations. Those are all broader types of mathematical models. But this is the type of model we've used so far in this class. And these models are used very broadly in the real world because they're so darn useful. Okay. So given a linear time invariant ordinary differential equation, before I go any further, here's like a little philosophical statement. Tell me if you agree. But So why do we model things mathematically? In my mind, the purpose is twofold. Oops. So number one, we model to predict. Wait, what's time invariant? Because part of the system changes with time. Very good question. Very good question. Like all of these differential equations, when we find the solution, I mean, the whole point of dynamics is that stuff changes with time. So why am I saying time invariant? Okay, so time invariant refers to the equation, the differential equation itself. So, for example, this is a time invariant equation. The mass of something times I can't talk. The mass times the acceleration equals maybe this force. Now, this acceleration is a function of time. This force is a function of time. But when we say time invariant, we mean that this equation itself, this differential equation itself, doesn't change as a function of time. Like this equation isn't going to become some other type of equation. Maybe I have to... Let me explain this a little bit. Like the dependent variable and the input are allowed to change with time, but something like this mass is not allowed to change with time in this equation. So maybe it's a little bit semantic in a way. So the dependent variable, which is x, can change with time. The input variable can change. So I guess okay, you say you understand it. Well, I guess what can't change is coefficients. FF7 again. You called it, Phil. Coefficients of the dependent variable can't change with time. Let me give you an example of a time-varying equation, and this will make sense. Think of, we just had the SpaceX Falcon launch, right? That has a time-varying equation because the mass of the rocket changes with time. Because as you expend fuel, you're losing mass. So a time invariant equation, the coefficients of the dependent variable can't change with time. So this is time invariant. This is time varying. So when you have these time varying coefficients, it gets nasty because the eigenvalue, or why do I can say eigenvalues. You know what they are. The eigenvalues of this system change as a function of time. The roots of the characteristic equation change as a function of time. For this system, you can solve for the roots. They are what they are. Okay. So why do we model things? I think we model it, first of all, to predict behavior. We want to understand things. We want to be able to predict the weather. We want to be able to plan for it. But the next step, and maybe more importantly, is we want to control. We want to bend things to our will. For good and bad. But I think this is why we model the stuff around us. Like, I make a model for a motor so that I can change the speed of the motor at will. And then I can put that motor on a car, or I can put it on a balancing robot, or I can put it on a manufacturing line. But I model it so that I can control it and predict its behavior. I don't know if you agree. That's my understanding of it right now. So you guys are learning to control the universe and predict the universe. Okay. Now, so this is where we started. So we look at the behavior of these kinds of equations, or the solution of these equations. And, well, there's two parts to a solution. Maybe I'll do a different color over here. Let's put this side over here. There's the particular part, and we'll come back to that. And we have the homogeneous part, because I think this is what we spent more of the class looking at. Okay, so you have a linear time invariant ordinary differential equation that describes some real life system. And what you can do from that homogeneous part is get something called the characteristic equation. And what do you get from the characteristic equation that's so important? You get the roots. And we know that there are just a couple different types of roots that you can get. I'll make a little box. You can get real, distinct roots, distinct meaning like different real numbers. You can get real repeated, and you can get complex roots. And we know that real distinct roots have a homogeneous solution that looks like this. It's like a1 e to the lambda 1t plus a2 e to the lambda 2t. And then the same thing for like however many roots you have. If you have repeated roots, it looks almost the same. And let's just call it lambda, because we'll assume all of these roots are the same. You'll have a2t e to the lambda t. And if you had like triple repeated roots, you're going to have like not t cubed, t squared. And it goes on and on and on. And if you have complex, you're going to have, let's write it like this. E to the sigma t, where sigma's the real part of the root. And then you'll have a1 cosine omega t plus a2 sine omega t, where omega is the imaginary part of the root. And you guys can write the homogeneous equation for any order system, because even a 100th order system is just built up of these building blocks. A 100th order system might be 50 second order systems put together. So making combinations of these is very easy. Or maybe not easy, but you can do it. Okay. Once you know the roots, you can tell me a couple things about the fundamental behavior of the system. And it comes from looking at these general forms. So the first thing we always check for is stable or unstable. And the way you distinguish, it's unstable if the real part of a root is greater than 0. Any root. It could be a 100th order system and it's just one of the roots that is problematic. Stable means that the real part of every root is less than 0. Okay, so first we just say, like, is the system stable or unstable? Because if it's unstable, we can't do anything with it. So for stable systems, we can look at how fast the system is. So let's say system speed. This is in terms of the time constant, which is related to the real part of the root. It's -1 over the real part of the root. That's our time constant. We can look at the oscillation frequency. Well, the damped natural frequency, that's the imaginary part of the root. We can also look at some other things, like the damping ratio. I don't know if you remember this, but the damping ratio tells you how much of an overshoot you have in your response. So like, well, we haven't talked about particular solutions in our flowchart yet, but if you have a second order system and you do a step response, you know, it'll shoot up and that first little peak will overshoot. The height of that peak depends on the damping ratio. So like all of this stuff, all of this behavior goes back to the roots of the characteristic equation. So those are super important. Okay. Oh yeah. While we're talking about roots, a convenient way of visualizing the roots is the complex plane. And you can look at different pairs of roots in your system. And for example, in this, it's real easy to pick out that these are our slowest system roots. So these are what we call the dominant roots. And these decay the slowest. So when you look at the response of this system, it's mostly going to look like these dominant roots because the other roots are going to decay to 0 and you're going to be left with these. That's why we call them the dominant roots. Now, when you have some idea of where you want the roots of your system to be, we didn't get to spend too much time with this, but we looked at the root locus. So this is also something in the complex plane. So you might have a parameter in your system, let's call it like k. And we want to see how the system roots change with that parameter k. The root locus is a tool for that. Like maybe your system has, maybe it's a third order system. And it has 3 roots like this. Well, we might see as we change k, like maybe these are where the roots are if you set k equal to 0. But if you increase k, these roots might move this way. And maybe this root just keeps moving off to the left. And so you can choose your parameter in this system. It might be like a spring constant, or it might be a capacitor value. And so you might make design decisions by doing a root locus plot. Root locus. Okay. Let's see. Okay, so all of this is without even considering inputs to a system yet. When we start to look at how like a control input affects a system, we're talking about the particular solution. And like the first rule, the particular solution is same form as the input function. So if your input function is a constant, the particular solution is a constant. If your input function is a sinusoid, your particular solution is a sinusoid as well. So like a good example, what we're doing right now is we're looking at the frequency response of a system. So if your input is a sinusoid, the particular solution is a sinusoid as well. Well, it's a sine plus a cosine, because it's the same form as the input function and the input function's derivatives. And you can also rewrite a cosine plus a sine as just a sine with a phase angle. And the complete solution, what if there are multiple input functions? Oh, for the particular solution? Then Are you talking about multiple inputs acting at the same time? If that's what you're saying, then the particular solution is the superposition of those different types. And we did some of that in the homework. Like, if your input is a constant plus a sinusoid, then your particular solution, how about we do it here? So like, let's say you have an input that looks like this, but you could just call this two inputs, a sinusoid plus a constant. Well, then your particular solution would be those sinusoids plus a constant. Yeah. Well, I think an important property of particular solutions is if we have a system and let's say I give it one input, U1, and what comes out is XP1, like my particular solution pertaining to that input. If I take the same system, it's important that it's the same here. If I give it a different input, then what comes out is XP2, a different one. If I say, okay, let's do both of these inputs together for the same system, then I get the addition of these two. So it's the superposition property. This only works for linear systems, by the way, which is one reason we love linear systems. Similar to the superposition property is the scaling property. Like if I give some input and I double its amplitude, well, you get twice the output. The scaling property. I just want to zoom out from here real quick, see what the heck I did. Wow. Okay, and then we remember the complete solution is the particular plus the homogeneous. Now we're running out of room on this page, but I want to include a couple things. We're not going to get everything on this flowchart. I mean, we did quite a bit. Let's see, where do I put... Maybe I'll put it right here. Let's use green. State space. So, state space, you take our differential equation and you put it into a form like this. It's a series of first order differential equations in terms of our states. Maybe I'll put 2 inputs for this one. So it's a really nice way of organizing our differential equations. I think for some systems, it makes it easier for modeling. And it definitely makes things easier for a computer. So whenever you're working with simulation tools, this is a good form for simulation. The reason is it's very easy to integrate first order equations. Even though this is a matrix equation, it's still first order. This is the first derivative of that state vector. So computers love to integrate first order equations. It's super easy. You can use something basic like Euler forward. Oh, there's a connection here. Let's draw it. Between roots and state space form. The eigenvalues of the A matrix equal the roots of the characteristic equation. Okay. And, okay, last one, and then we'll be done with this flowchart. What other color can I choose? Choose this. We also started talking about transfer functions. Now, when you define your outputs, inputs, a transfer function is the Laplace transform of your output divided by the Laplace transform of your input. And this is y of s over u of s, and then often we call that g of s. It's very common to call a transfer function g. Now, why did we bother coming up with yet another way of representing a model for a system? Like, we have differential equations, we have state space, we have transfer functions, we have like 3 different ways. Why? So I think the advantage for transfer functions has to do with the relationship to the frequency response. And this relationship makes it easier to get models for real-life systems from experiments. So we did an experiment. We got a model for a motor, a DC motor. What we did is we provided different sinusoidal input frequencies. So that's voltage, that's the input for the motor. And looking at the response, the frequency response, I was able to fit that with a transfer function. So it's good for modeling from experiments. And I guess it comes down to this equation. Your steady state output is, like I've showed you this formula, you'll see it again today. The amplitude of the input times the magnitude of the frequency response function, sine omega t plus the angle of the frequency response function. And the frequency response function comes from the transfer function. So these you can get from experiments. You can directly measure them from a real life system. It's beautiful. And let's make another connection here. Because the poles of a transfer function are equal to the roots of the characteristic equation. Poles equal roots. So there's if you have one of these three representations, you can convert between them. Actually, I think that's what we did at the end of last class. We got a transfer function for the motor, and then we converted it to a differential equation. And if we wanted to, we could convert it to state space from there. That's one thing I like about dynamics. It's all connected. And these different representations tell you different things. Wow, what a tangled web we have made. This is what the inside of your brain now looks like. Just a jumble of connections. It's pretty cool to go back, reflect on what you've done, see how things are connected. You guys have accomplished a lot. I'm proud of you. Did a lot of hard work. You'll be able to apply this to a lot of different things. It's very broad. So I hope you enjoy putting together a flowchart. I think that's really helpful from time to time. Okay, guys. Today, we're going to get into a little bit of new content, layering on our knowledge of frequency response functions. I want to talk today about how you can think of a dynamic system as a filter. And you can use it as a filter. So let's start with this example. If you have a linear dynamic system and you give an input that is a sinusoid with some amplitude, the steady state output will be this. And this is the magnitude of the frequency response function. This one is the phase of frequency response function. And what you can do you can plot the magnitude and phase on two separate plots, and we call that a Bode diagram. So this magnitude is 20 log base 10 of the magnitude of the frequency response function. This one is the phase, and it's converted to degrees. Okay. So let's show how you can use this plot. There's a couple ways. So one question is, what is the steady state output of this system if the input is given by this sinusoid? So the amplitude is 5, the omega is 100 radians per second. Well, I know that the steady state output is the amplitude times the magnitude of the frequency response function times sine omega t plus the phase. And another way we write the phase is with the Greek letter phi. So I'm going to use these plots to get this information. So I have to look on this plot where omega is 100. So 10 squared is 100. So let's just like make a line there. Okay, so the magnitude is going to be here. The phase is going to be here. Let's start with the magnitude. If I draw a horizontal line across, that looks pretty straight. I'm going to guess this is around 17 decibels. Okay, so, but when I plug in the amplitude of my frequency response function in here, it shouldn't be in decibels. So, in other words, (17) equals 20 log base 10 of the magnitude. So that means log base 10 of the magnitude is 17 over 20. And then solving this logarithmic equation, that means the magnitude is 10 to the 17 over 20. What is that? I'm going to go into MATLAB. 10 to the 17 divided by 20. So that's 7.08. So you can get that off a Bode plot. Let's look at the phase. I'll draw a horizontal line here. I'm going to say that's like 30 degrees. Now, but when we plug in a phase into the sinusoidal expression, it should be in radians. So to convert this to radians, we multiply it by pi over 180 degrees. So pi divided by 6. Well, we could just call it pi divided by 6 radians. That's nice. Okay, so looking at the Bode plot, I know that the steady state output of this system is going to be 5 times 7.08, and then it's going to be sine omega is 100t, and then plus pi divided by 6. So you can use this plot to, predict what the output's going to be at a given frequency of input given a certain amplitude. Okay, now let's interpret this plot more broadly. What range of frequencies, for what range does this system behave as an amplifier? Now, all an amplifier means in terms of signals, this means that the output amplitude is greater than the input amplitude. And this is beginning to shape looking at a system as a filter. If we have a dynamic system and I provide some sinusoidal input, my output might be larger amplitude. We call that an amplifier. So this is asking if we can rewrite this in a different form. For what range of frequencies is this amplitude greater than 0? That's another way of asking for what range of frequencies does this behave as an amplifier. Or wait, this should be greater than 1. My bad. Because the output amplitude is the input amplitude multiplied by this factor, right? So if this factor is bigger than 1, then I amplified the signal. Well, that would mean, for this plot, the plot's in decibels. So if you take 20 log base 10 of 1, log base 10 of 1 is 0. So if we look at this decibel scale, we're going to be amplifying if the decibels is greater than 0. So we need to find where 20 log base 10 g I omega is greater than 0. Let's look at the plot. So what I can do, I can look at this 0 decibel line, and from, it looks like about here to here, the line is above that 0 decibel mark. So this system, whatever it is, it could be a mechanical system, an electrical system, but for this input-output relationship, this behaves as an amplifier over this range. Over this frequency range. So what is this frequency range? Like here to here. Let's keep tracing it down. Let's say it follows this line. Okay. So this right here is 10 to the 0, which is 1 radian per second. This next line, I don't know if you can see it, it's a little faint. That's 2 radians per second, 3 radians per second. This is 4 radians per second. And this one is, well, it's right at 10 to the 4th. So 10,000 radians per second. So if you give an input to this system that has a frequency between 4 and 10,000 radians per second, the output is going to be amplified relative to the input. So this acts as an amplifier for 10,000 radians per second. Any inputs with frequencies in there, we're going to have an amplified signal. Okay, I'm going to introduce the idea of bandwidth, and then we're going to go on a break. You probably heard the word bandwidth before in different contexts. Like, what's the bandwidth of my, I don't know, cell phone service, bandwidth of my internet. That's a little different than the way we talk about bandwidth when it comes to filters. So let me first draw it on the graph, and then we'll try to put it into words what it is. So first of all, a bandwidth is a specific range of frequencies for a filter. And the way you find the bandwidth is you identify the highest amplitude or the highest magnitude on here. So I'm going to draw like a horizontal line up here that passes through the highest point. And maybe this is, let's just call it 19 decibels. Okay, so you find the highest point, then subtract 3 decibels from that. So that would be 16. Draw another line at 16 then. So maybe we'll put it here. So 19 minus 3 is 16 decibels. Okay, the bandwidth is the range of frequencies for which this magnitude is above this line. So this right here is the bandwidth. If I'm in between these frequencies, my amplification will be within 3 decibels of the maximum value. It's a little hard to put into words. So, okay, let's identify the bandwidth here. Let's just try to draw it in. I probably made that line crooked. We won't worry about it too much. We'll say it goes here. So I'll say this upper end of the bandwidth is 10 to the 3rd. And we will say this one, this is 10 to the 1. So that's 10, 20, 30, 40, 50. And I'll say, okay, 50. Okay? Let's see if we can describe that in words. Okay, so first of all, it's a range of frequencies for which the amplification is within 3 decibels of the maximum amplification. Okay, I feel like that's pretty good. That wasn't too hard. So in this case, the max amp, 19 decibels. Therefore, max minus 3 decibels is 16 decibels. Therefore, bandwidth is... I don't remember what frequencies I listed. Between 50 and 1,000. So 50 bandwidth less than 1,000 radians per second. Now, why do I introduce bandwidth? Because it's a popular term, and it's one way that we classify what type of filter a dynamic system can act as. So we're going to take a 5-minute break, and I'm going to come back, and I'm going to describe some classic types of filters that dynamic systems can be. And we'll try to talk about how it's related to the bandwidth of the filter. Okay, so I got 3:08 Eastern. We're going to come back at 3:13 Eastern. I have 2 cool examples. So stick around. It's going to be fun. Okay, we'll be right back. about we talk about some different types of filters? All right. We're getting back into it. Okay. So I have a grid here. I'm going to show you 6 types of filters. And for this last one, which has a cool name, the anti-resonator, I'm going to show a musical example. So we'll get there in a second. Okay, so you have a dynamic system. It could be mechanical, it could be electrical, it could be digital. We're going to make a digital system today. But you have inputs, you have outputs, and the input and output quantities could be totally different things. Like when we were controlling the DC motor, the input was a voltage and the output was an angular velocity that I was measuring. So they could be physically different quantities. But the signal profile itself, you could think of this system as filtering the input and creating some other output signal. So we're thinking of dynamic systems as filters. Let's talk about a low-pass filter. Oh, and why I mentioned bandwidth is filters are often classified by their bandwidth. Let's look at a low-pass filter. I'm going to draw the magnitude plot. So this is going to be 20 log base 10 of g I omega. So that's going to be the vertical axis. And the horizontal axis is going to be frequency. So a low-pass filter looks something like this. Look familiar? This is the type of plot we had for the DC motor. This is also what the plot will look like for an RC circuit. If we draw the bandwidth on here, you would find the maximum, which is the max is here. And then if you go to the maximum minus 3, maybe it's like here, then our bandwidth is this. So the bandwidth is like from 0 up to some number, some frequency. Let's call it omega naught. So we could say if a filter has this kind of bandwidth where its highest amplification is at low frequencies, we call it a low-pass filter. And a transfer function for this low-pass filter might look like this, which is the type of filter we use for the type of transfer function we use for the motor. We call it low pass because it amplifies low frequencies and it attenuates high frequencies. So if you give a high frequency input, like if omega is going this way, well then you might have negative decibels and the output signal will be much smaller. Okay. What about a high pass filter? Can you guess what this might look like? If you've seen a low pass, it could look like this. And if you were to find the bandwidth on this, so here's maybe my maximum. And then I subtract 3 decibels. In this case, well, it looks like the bandwidth just goes on and on and on to the right. Let's call this low end omega naught. So in this case, the bandwidth has a bottom end. And for this particular filter, we might say the bandwidth goes all the way to infinity, assuming that this looks the same the rest of the way. So we call this a high-pass filter because it amplifies high frequencies and it attenuates low frequencies. But this classification is based on the bandwidth, where the bandwidth has a clear lower end, whereas for a low-pass filter, the bandwidth has a clear upper end. Higher frequencies are outside of the bandwidth. They're not amplified. And for this, lower frequencies are outside the bandwidth. This particular one that I just drew, it's going to look like this. It has an S in the numerator. I'm going to build a filter like this for you today. And it has a practical purpose. We're going to use this filter to make a custom radar gun to measure speed. Believe it or not, this filter can measure speed. You'll see. Okay. Bandpass filter. To save time, I'm going to stop labeling these axes. I know, it's a taboo. But they're all the same. Bandpass. It might look something like this. Look at the bandwidth in this case. The low-pass filter had a clear upper end. The high-pass filter had a clear lower end. A bandpass filter has clear lower and upper ends. Let's call this omega naught and omega 1. Bandwidth. So a bandpass filter, its bandwidth is only over a certain range. It only effectively amplifies a set range of frequencies, a finite range. A notch filter is similar to a bandpass filter, but it's kind of inverted. Let's draw it like this. You can see it kind of has a notch in it. That's why we call it a notch filter. If you find the bandwidth, so we find the maximum amplification, which actually happens at a couple places. And if you take the max minus 3, you get this. And you see that the bandwidth goes over 2 distinct regions. Let's call this like omega naught and omega 1. So for this notch filter, the bandwidth, it goes from 0 to omega naught. And let's say it this way. And it goes from omega 1 to infinity, assuming that that trend holds. So the way to think of a notch filter is it attenuates a specific range of frequencies. You put a certain frequency into this system, in the output, it's going to get attenuated. It's going to become smaller in amplitude. Bandpass, I guess we didn't write that earlier. It amplifies a specific range of frequencies. So we got low pass, high pass, band pass, notch. Okay, these next two are kind of interesting. Let's draw a resonator. The pendulum that we modeled at the beginning of this class is a resonator. If you look at its frequency response, there's a specific frequency where the amplification just shoots way up, and we call that resonance. And then it drops way down after that. But this happens close to the natural frequency of the system. If you had to classify the type of filter that this is, based on the previous four, like we would call this a resonator, but if you had to call it low pass, high pass, band pass, or notch, what type of filter would you call it based on its bandwidth? And I'm going to write a transfer function for this on the side, just so you have some idea. Any takers? What type of filter would you call that? Based on the 4 classifications up above. It'd be a bandpass, right? You'd find the maximum amplification, it'd be somewhere up here. You subtract 3 decibels. And then you just have like a really tight range. Okay. Let's do an anti-resonator. It looks a lot like this one, but it's like inverted. It has this really deep notch in it. And then it like amplifies up after that. And in this case, the transfer function is, it's the inverse of the other one. So it has this really deep gouge in it at the natural frequency. Okay, I'm going to show you a fun example, a musical example of the anti-resonator. So I have to pause our other background music. Oops. And I'm going to go to MATLAB. Now, you may not know this, but you can use MATLAB to play music using, what command is it? The sound command. Okay, so let's just play this and then I'll explain it. Okay, do you hear that little excerpt? So, this graph is the sound file. And if you zoom in, you're going to see it's like sinusoidal. Well, actually, there's 2 signals here. The black line is the original sound file. So when you create music, it creates, pressure waves. Those interact with your ears, and that's the sensation of sound. So this sinusoid as a function of time is a representation of that pressure wave. It's the music. Okay. So what I did is I corrupted this sound file with this red line. I'm going to show you what it sounds like with the corruption added in. It doesn't sound as pleasant. So what is this corruption? I put in a sinusoid at, I called it an annoying noise at 800 hertz. So like an A. Oh, was it really loud? Oh, because I have my headphones turned down. Oh shoot, was that really loud? I'm sorry. That wasn't too bad. Okay, so anyways, I corrupted my music. What if I want to use a filter to get rid of this corrupted sound? So, let's see here. Let's advance this code a little bit. So I made a filter. And it looks like this. So this is an anti-resonator. This is the magnitude part of a Bodhi plot. And you'll see, like, for different input frequencies, the amplification is 0 decibels, meaning for low frequencies, this filter does nothing to the signal. If you give some input signal, the output signal is going to be the same. But as you get to higher frequencies, specifically this frequency right here, which is at 800 hertz. Dr. Strudel, I'm editing my next album only in MATLAB. I love it. I love it. So I made a filter that heavily attenuates that specific frequency. Like it goes down to minus 80 decibels. So minus 80 decibels. What does that mean in terms of reduction? Let's do a quick calculation. So minus 80 is 20 log base 10 of, let's call it like whatever this percentage reduction is, or whatever it is. So R is minus 4. Wait. Any chance you could send us that code? It's pretty cool. Sure. I would love to send you this code. Yeah, you can play around with it. You could import your own sound files and play with like a filter. Okay, so minus 4 is log base 10 of R. So R is 10 to the minus 4. So what this filter means is at that nasty corrupted frequency, that input should be reduced 10,000 times by this filter. So let's see what happened to that annoying signal when it went through this filter. Original. Oh, I have to fix this plot. Original. I think this is the noisy signal. So let's go back here and fix that legend. Oh, I want to switch these colors to be consistent. Okay, we'll try that again. Okay. So let's get in here. So the red, that was the corrupted signal. Let's zoom in a little bit more. The blue is when I sent it through the filter. And now you can see the original signal is here in black. And so when I went through that filter that tried to surgically remove that, 800 hertz nasty extra sinusoid, it does a pretty good job. Now it it doesn't look the same as the original, right? And that's because if you look at this filter, it doesn't just affect that one frequency. There's kind of like this, it affects some frequencies in the neighborhood as well. Okay, so let's listen to the sound file from the result. See what it did. Huh? So you don't hear it anymore. Let's go through the process again. I'll just like rerun the code. Hopefully it doesn't blast your headphones too bad. So this is the original. Now we're going to corrupt it. So that's that 800 hertz. It totally ruins the song, right? And then we put it through the filter. And we basically get the same sound back. It sounds like a little more muffled, I guess. We didn't perfectly preserve the music. Okay, I'll post that code. If I forget, remind me. Sometimes I forget to post things like that, but don't let me forget. I would love to share it with you so you can play around with it. Okay. So that's an example of one use of an anti-resonator. If you have a specifically nasty frequency that you want to remove, you know, I have another great example of an anti-resonator. Your washing machine. Have you guys ever had a washing machine that just like wobbles all over the place? And it's like doop, 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 doop. Shakes the whole house. So, like when people make a washing machine, they try to build into it anti-resonant properties. So the frequency at which your washing machine wobbles around is the frequency of the spin cycle. I don't know how fast the spin cycle is, right? But it's moving, right? So that's the one frequency where it can start to like shake your whole structure. So you can build in anti-resonant properties so that at that specific frequency, we try to attenuate the movement of the washing machine. So that's like a mechanical anti-resonator. Cool, right? Okay. Okay, we're going to do another example. We are going to build a desktop radar gun. Let me show this thing to you first. Let's get this plugged in. I don't know if you've seen an ultrasonic range sensor before. A lot of little robotic kits have them. But it looks like this. It looks like a little like Wall-E. It's got like two eyes. Well, one of these is an ultrasonic transmitter. I think it's, it's this one. You can see there's like a little T down there. T for transmitter, I believe. And then the other one is the ultrasonic receiver. So this sends out ultrasonic, like high frequency sound waves. They bounce off of whatever you're pointing it at. And based on how long it takes for those waves to travel back, it can tell you how far away whatever it is you're pointing it at. And this doesn't work over like very long distances. It's probably just up to a couple feet. So I have it plugged into the Arduino here. Let's open up this code. Let's run it. And then I'll show you the output here. Well, maybe I can use this other view. Let's try this. Oh, okay. We'll try multiple cameras with this. Okay, so I'm gonna go over here, go to this plotter. Okay, cool, you can see like a signal. So I'm pointing the ultrasonic range sensor at my computer screen, and I'm moving it towards it, and you see the signal is changing depending on the distance. The signal is in inches. So like right now it's about 8 inches away, and if I move it back, now it increase to 15 inches. So this is transmitting ultrasonic waves. It's counting how much time it takes for it to come back. And that's how it works. It measures distance. Have you guys seen one of these before? Look at that guy. If I point it at the ceiling, I'm pointing it straight up, it went up to, well, I don't know what the heck it's saying. It's saying like 33 inches, but it's definitely, actually that might be accurate, I don't know. Ceiling's 3 feet from me? Maybe. What about this wall behind my computer? 15 inches? I don't know, but it gets less accurate the farther away it is. So look at this though. The signal's a little bit noisy. You see how it kind of bounces between different values. So take note of that. Let's pause this for a second. If I go. Get back to here. Ooh. Okay, so I'll show you one thing first. So noise is a high frequency disturbance added to your original signal. It's just like the sound file that I corrupted, right? I added a sinusoid. Well, noise is like adding a really high frequency sinusoid. So excuse me. One way to get rid of some of that noise is to use a low pass filter. So a low pass, like if the noise is high frequency, then all of those high frequency sinusoids that are superimposed on your signal, they get attenuated and they disappear, whereas the original signal is preserved because it's low frequency. So I want to show you, I have a low pass filter that I built into here. And I want to show you both signals in real time. We'll go back to like this multiple view kind of thing. And we'll plot this. And now it should show 2 signals at once. Give it a second here. See the red signal? It's very smooth. That's the low pass filtered signal. So the blue is the original signal. It's like the input to my filter. The red is the output of a low pass filter. Notice the low pass filter though, there's some phase lag. Like it's delayed a little bit, which makes sense, right? We talked about phase delay. Like the blue is the input, and so the red must react to it, so it's a little bit delayed. But isn't that cool? You can see that the noise is certainly attenuated, and it just comes at the expense of some phase delay. But I can even change the cutoff frequency or the corner frequency of my filter. Maybe I'll make it like, I don't know. I'll make it a little less aggressive of a filter. Let's see how that looks. Now there's less delay, and it still looks like a beautiful, smooth signal. Isn't that cool? Okay, now let's get on to, because this isn't all I want to do with this, I want to build a radar gun. So I want to measure how quickly, like right now it's measuring position. So I'm saying I want to measure velocity. I want to be able to point this at my computer screen and have a filter that tells me how quickly I'm moving towards or moving away from the screen. That sounds like a cool idea, right? Huh? Okay. So we're going to do it. Okay. We're going to do it. And what we need to do it is something called a differentiator. A differentiator, you guessed it, a filter that calculates the derivative of the input signal. So the input is some signal, and the output of this filter is the derivative of that signal. So that's exactly what I need, right, to make a radar gun, to measure speed. The sensor measures position, and I'll call position my input signal. And then I want the output to be the speed. So the transfer function for a differentiator is kind of simple. It's S. G of S equals S. There's some problems with this. We'll talk about it. But let's take an example of a sinusoid. So if this goes into a differentiator, G of S equals S. Well, what should come out? The derivative of this is A omega cosine omega t. So that gives you the concept here. Now, cosine, you can write it in terms of sine. You know that, right? It's sine plus 90 degrees. Or you could equivalently say it's sine omega t minus 3 pi over 2. So notice the input amplitude was A. The output amplitude is A times omega. So this frequency omega is the amplification. If you have a really fast omega, so omega is really a big number, your derivative is amplified a lot. If the frequency is really small, well, the opposite happens. And then here's the phase shift. So all I'm trying to show you is that taking the derivative of a signal is the same. I mean, it involves some amplification and some phase shift of the original signal. It's easy to see with the sinusoid. But remember, I don't know if you've probably studied this at some point, but any signal can be represented with sinusoids, even if it's a really complex signal. That's the principle of the Fourier series. So all that to say that what I'm showing you with this example of a sinusoid, that happens for any signal. So this radar gun that I'm making, it's not just going to be for purely sinusoidal motion, it's going to be for anything. Okay, we're going to fill out this table first. This shouldn't take too much time because this is a very basic transfer function. So G of S equals S, so G I omega equals I omega. And if I take the magnitude of this, which I'm going to calculate here, that's the square root of the imaginary part squared plus the real part squared. So this is just going to be omega. If you square it, then take the square root. It's just omega. So that's easy. The amplification is the frequency itself, which is what we identified here, right? Whatever the frequency is, that's how much the derivative gets amplified. 10 to the 1. I'm just going to write this as, that's going to be 1, that's going to be 10, this is 100, this is 1,000. This is 10,000. Now, when we do the Bode plot, we convert this to decibels, right? So you take 20 log base 10. 20 log base 10 of 10 to the minus 2. This is minus 40. 20 log base 10, 10 to the minus 1. This is minus 20. This is 0. This is 20, 40, 60, 80. So why don't we plot that on this one? So at 10 to the 0, it's 0 decibels. 10 to the 1, it's at 20, and then 40. Oh, wait, I marked the wrong one. 40, 60. So the frequency response is just, the bigger the frequency, the more it gets amplified, right? Just like a kind of simple trend. The higher the frequency content of the signal, the more the derivative is amplified. Okay, let's do the phase. The phase is also just the angle of the frequency response function, which is the tangent inverse of the imaginary part over the real part. So this is going to be the inverse tangent of omega over 0. So we have this divide by 0 thing here. So this is going to happen no matter what omega is. You're always going to have this divide by 0, and so it's 90 degrees for everything. That's the case where that happens. And look up here. When we did the derivative of a sine, we got a phase shift of pi over 2, which is 90 degrees. No surprises there. You could also write it as minus 270 degrees, which is 3 pi over 2. So doing the phase plot is just this. It's 90 degrees for all frequencies. Okay. So if I want to make a filter that calculates the derivative, I want it to have a frequency response like this. I don't know. It's a little abstract to be like, I'm building a filter that differentiates any signal. I mean, doesn't that sound kind of strange? Like, how could it accommodate everything? I don't know. It's interesting what we're doing, and it's kind of hard to wrap your mind around. But taking a derivative operation is fundamentally like having a filter that has a frequency response like this. Just go with it, okay? Okay. Well, how would I even implement a differentiator? Like, I want to run this on an Arduino. How do I build it? You guys have built differentiators before. You might not have known it, though. And it's all built on this simple principle. The time derivative is the change in a variable divided by the change in time. So let's say, I don't know, we have a function f as a function of time. And let's say I want to get the derivative right here at, let's call it t naught. Well, we know the derivative is the slope right here, right? Okay, so calculating the derivative on a computer is like calculating the slope, but you need you need 2 points to do it, right? I don't know. Let's make another point here. And let's say it's t minus 1, because it's like one, let's call it one time step prior. Well, because this is kind of far away, well, first I'll write my approximation. You might see where I'm going with this. The derivative of this function at t naught is approximately, so I'm using this change in the variable over change in time. So the variable changed this much. It started at whatever value it was at t minus 1, and then it increased a little bit. So like over here, this is f at t minus 1, and this is f at t naught. So it changed this much, the difference between the two, and this was the change in the time. But you can see just from this figure, because these points are separated a little bit, it's going to say that the derivative at this point looks like this, which is steeper than I think it really should be. So, one problem with calculating the derivative in this way is the time steps should be close enough together to really, capture the profile of the signal accurately. But there's another problem. And this is the issue of noise. I'm going to copy this whole thing, if it'll let me. Copy. Like, let's say that's the true signal, that brown line. I'm going to get rid of this. Let's fill that in a little bit. What if I superimpose noise on this? Now you saw when I plugged in my range sensor with the Arduino, the signal was a little bit noisy. And having noise is kind of just like, I don't know, drawing some random squiggles on top of your original line. Now, what if I wanted to use the same formula for approximating the derivative, but on this noisy signal? I think you can see, if I take like f at t naught, I might pick this point, like at the top of that peak. And if I pick f at t minus 1, I might pick down at the bottom of this peak. And it's totally unpredictable, right? Like this electrical noise or whatever it may be, it is what it is. And if this was the case, I would way over predict the slope. And you know what? Even if I sampled, if I squeezed these time measurements closer together, it wouldn't get any better. In fact, it would get worse. Like, what if I put my measurement right here? Like, what if instead I called that t minus 1 and I had a measurement here? Well, if I connect these two lines, the derivative is even more off. And it's extreme. It's really high. The slope is very large. What I'm showing you, which makes intuitive sense, it connects back to the plot we made here as well. Because noise is high frequency. So derivative gets amplified with noise. Like from that picture I was making, you can see how it's happening. Like you connect 2 points that are very different over a short amount of time. That's a big derivative. But it's also explained with this frequency response where it's saying like, look, I know that's going to happen because you're describing points that are rapidly changing. Well, I mean, that's another way of describing frequency. It's something that's oscillating very quickly. That's what noise does. And it oscillates very, like every time you sample it, it's going to be something different. So, what I'm saying is, if you want to build a differentiator, something that differentiates any kind of signal, you can use a formula like this. And it's very easy to program. The problem is, if you try to use this in real life, you're going to get a crazy signal. Let me show you. Let's plug this thing back in. And I'm going to try to make our radar gun using that formula. What do you think is going to happen? And will it be good or bad? By the way, you guys should totally get an Arduino. If you just Google Arduino projects, I guarantee you would find one that you enjoy. I have a lot of fun with this. Okay. Plus, it's going to make you a better engineer. All right, let's look at this. See, I'm moving it slowly towards the screen, and I want to calculate how quickly I'm doing that. But look at my signal. I'm using just a raw differentiator, using that approximation I showed you, and it gives me back garbage. The signal makes no sense. Okay, so what do we do? Obviously, there must be something we can do, right? Okay, I think this is really clever. I didn't come up with it. But this is how we differentiate things in practice. Okay, first I'm going to draw what the frequency response of a differentiator should look like. It looks like this, right? That's just what a derivative is. There's nothing wrong with that. The problem is, if there's noise in a signal, it's going to be high frequency and it's going to get amplified. But I'm not trying to take the derivative of the noise. I'm trying to take the derivative of my low frequency signal. So somebody had this idea. I don't know who it was. What if I have a differentiator for low frequencies, but I make it an attenuator for high frequencies, like where noise is going to be involved? So let's say that the frequencies that I expect let's say the frequencies that aren't noise, like I know this is something real that's happening, is like between up to like 1 hertz. So that's saying, like, let's say I'm moving this device from my computer screen. I don't expect to be doing that any faster than 1 cycle per second, right? Or if I'm just moving it forward, it might not have like hardly any frequency at all. I'm not moving it back and forth. So I'm like, look, I only need to go up to like 1 hertz here. Anything after that, it might be noise. So what if after this, I make it an attenuator? Like, what if the frequency response instead did this? After that point, it just dropped off. You see what I'm saying? So up to this point, I'm saying don't change it. Put it on this line that is a differentiator. But after that point, I don't care what you do to the signal. It's all noise. Let's attenuate it. So the way you can get this effect where the amplification drops off after a certain point is you can superimpose a low-pass filter on this. So I'm going to erase this, and I'm going to draw a low-pass filter. I'm going to draw one that looks like this. And then at the corner, it's going to drop to like -3, and then it's going to go down -20, like each. Okay. So this one the differentiator, the transfer function is g of s equals s. This one, we've studied this one. This shape looks similar to what you've seen. This is 1 over a corner frequency s plus 1. And here I made the corner frequency at 10 to the 0 equals 1. So the corner frequency is 1 here. So what I'm saying is, if I make a new differentiator and it's s, so the original differentiator times 1 over omega cs plus 1, then the combined plot is going to behave like this. You just add the red line to the blue line. So the blue line is 0 at this point, these lower frequencies, so it doesn't even affect the red line. But after this corner frequency, the red and the blue line are equal and opposite, and they cancel each other out, and the net response is this. So maybe I'll make this extra clear. This is the combined frequency response. It behaves like a differentiator up until this corner, and then after that it has an amplification of 1. So it preserves, like even if there's noise, I mean it won't attenuate the noise, but it won't amplify it either. So how about we see how this filter works? Okay, so we're going to I'm going to add this one in. So this is going to compare the two. So I added a low pass filter to my differentiator. Oh, I unplugged my sensor. Okay, let's get this ready. So, okay, it'll get there in a second. Okay, so the red line, it looks a little better, but it's not attenuating the noise enough, I think. It's letting the noise through, and it's not squashing it enough. But you can still see, like, it makes more sense than it did before. Well, and the blue line just had a huge spike. So what I'm going to do is add one more filter. So this is what's cool. I wish I had like 2 more weeks with you guys, but you can double the effect of that low pass filter by adding like another one. So if somebody looks at this after the lecture, it'll just look like a glob, but I hope if you're following along at this point, it's making more sense. But if I add another one of these blue lines, I double the effect, and now the combined plot is going to actually start attenuating that high frequency noise. Now this is going to be sweet. So this is our next level stuff. Next level. Okay, tools. Plotter. So I'm moving this towards and away. I think it'll get better in a second. The scaling of this graph, that is. Okay, it's getting a little better. I'm going to do one more thing here. I'm going to reduce this cutoff frequency to this. And then I'm just going to show this velocity filter by itself, because then it'll look really pretty. Okay. This now is the velocity smoothed out. It's in inches per second. So the scale on the left might be too small for you to see. Actually, I think it's cut off the screen. But this, I'm moving it between 0 and like 6 inches per second. Let's see if I can just constantly move forward at some constant rate. So very cool. We made a filter that calculates velocity with this little guy. Okay? It measures position, but I sent that position measurement through a filter that grabs us that velocity. I know we went a little long today. I just wanted to show you, I don't know, as many examples as I could. We did some fun examples. We did some music filtering. We made a filter that differentiates a signal. We dealt with noise. Man, there's just so much you can do with system dynamics, my friends. Guys, that's going to be it for the... I'll turn on some music here. Oh, we need something a little more upbeat. But that's it as far as the content. Now, if you're somebody who's like, I really enjoyed dynamics, what do I do next? I think that probably a control systems course is for you. If you're at UB, we have continuous control systems offered in the fall. I teach digital control systems in the spring. If you're going to graduate school eventually, there are so many controls courses you can take. And man, but dynamics of anything, if you're going into road vehicle dynamics, I teach that in the fall. Flight dynamics I'm going to be doing in the fall. We're going to build on this theory. Man, and if this is your first time taking like dynamics, there's so much to assimilate here, so don't feel like, oh, I don't get it yet. Well, it takes years and years and years to get it. You just got to keep practicing. So I would just say, if you enjoy this stuff, if you find it intriguing, keep with it and keep looking for opportunities to study it more. And if you ever have any questions for me, you have my email. Shoot me all your questions. I'd be more than happy to help any of you out with whatever you need. If you want some advice. But I've really appreciated this course with you guys. It's been fun. I think you guys do great work. So, like, what's left for the course is we have one more project. That's all we're going to be doing for the rest of this week. That project is either going to be up tonight or it's going to be up tomorrow morning. And I'll give you some deadline on Friday. And it'll be reasonable to complete in that time. You won't be able to reach me on Twitch. Unless I don't think I'll be able to set it up, but you can always email me. Shoot me an email and I'll get back to you. Yeah, let me know if you have any questions. I'm going to hang around here until about 5 p.m. So you're more than welcome to hang out as well. Ask me any questions you have. But thank you guys once again. I hope you've enjoyed this course. Do me a favor, fill out the course evaluations. Let me know what you like, what you don't like. I use that feedback to improve the course. The feedback is anonymous, so don't worry. I won't know who it is. Give me your honest opinion. Tell me what worked, what didn't work. I'm trying to improve this class and make it better each time. It's kind of like when you watch Bob Ross. You guys like watching Bob Ross? If you look at some of the early seasons when he's painting, like by the time you get to season 18, season 20, his painting improved so much. So I want to be the same way. 20 years from now, I want it to be way better than it is now. And your feedback is going to help me do that. So I'd appreciate it. Thank you so much. Oh, I gotta post that code for you. forgot to add this to my evaluation. I thought homework after every class wouldn't be fun, but it really helped me stay on track and master material. This was a fun class overall. Thank you so much for saying that, Olivia. Yeah, I figured because this course is so quick and because it's so fast paced, it's just best to try to keep people on track. Like you said, I think it's like it forces you to stay on track if you have to do some homework each time. So I'm glad you like that. Yeah, I know it's like, oh my god, there's so much homework, but I think it makes it easier by the time you get to the end. Like it's like working out. You get into the habit, and then it's not so much of a burden after a while. Alright, everybody, I gotta run to a Zoom meeting. Once again, thanks for all your attention this summer semester. I'll see you around.